What is the probabilistic framework behind VAE uncertainty? Imagine trying to predict what a blurry photo might look like if it were sharper. Variational autoencoders do something similar. They generate clear images from fuzzy data by understanding the uncertainty involved. Now, how do they do this? Let's break it down. Variational autoencoders are a type of generative model that use probability to understand data. Unlike simple autoencoders that compress data into a fixed point, VAs encode data as a whole distribution. Think of it like describing a shape not just by one point but by a whole cloud of points. This approach helps VAs capture uncertainty in the data and how it can vary. At the core, VAs assume each data point is created from some hidden or latent variable that follows a prior distribution, usually a Gaussian, which is a bell curve. The encoder network then learns to approximate the posterior distribution of these latent variables based on the input data. Instead of giving a single fixed code, it outputs parameters like the mean and variance of this distribution, showing how uncertain the model is about the data's true representation. The decoder then samples from this distribution to reconstruct or generate new data. This sampling step is key because it allows the model to produce different outputs from the same input, reflecting the inherent uncertainty. When training VAs, the goal is to maximize something called the evidence lower bound, or ELBO. This involves balancing two things. First, how well the generated data matches the original, called the reconstruction loss, and second, how close the learned latent distribution is to the prior, measured by the Kolbeck-Leibler divergence. This second part acts like a Ruggitzlause, preventing the model from overfitting and ensuring the latent space remains smooth and continuous. Now let's talk about uncertainty. VAs split it into two main types. First, aleatoric uncertainty, which is the randomness in the data itself, like noise in a photograph, that can't be reduced no matter how much data you gather. Second, epistemic uncertainty, which stems from limited knowledge or data, meaning the model isn't sure because it hasn't seen enough examples yet. Some advanced methods extend VAs by explicitly separating these two types of uncertainty, making the models more interpretable and reliable. This is especially useful in areas like medical imaging or autonomous systems, where understanding the confidence in a prediction is vital. In practical terms, this probabilistic approach allows VAs to generate a wide variety of outputs, quantify how confident they are in those outputs, and recognize when they are unsure, like spotting a blurry or unfamiliar image. This makes VAs powerful tools for applications such as image creation, anomaly detection, and even in large language models that generate text. To sum it up, the probabilistic framework behind VAE uncertainty is about encoding data as distributions, balancing reconstruction with regularization, and breaking down uncertainty into its fundamental parts. This approach lets models produce diverse, realistic outputs while also providing a measure of how certain or uncertain they are about those outputs. It's a smart way to make AI systems more flexible, trustworthy, and capable of handling real-world complexity.